Okay, if you have a trapezoidal graph, which is the altitudes and the x values, you can clearly label the slopes and the areas. Okay, slopes with rectangles, areas with circles. Okay, there are two other things that are well worth labeling that really kind of encompass the main ideas you run into in calculus and in interpretive graphs and all kinds of things. Okay, so the one thing is the accumulated areas. Well, by accumulated area, the accumulated area through the end of the first trapezoid is 34 because that's all the area you have between here and here, area 34. So accumulated area is 34. And then to that, we add the 28 to get 62, and that's the area that's accumulated between the left side and the end of the second partition. Then we add the area 12 to that, and I didn't label it because there isn't room to label it, but it's very easy to label. And we get, I'll just put the number down here, it's going to be 74, and a little arrow here to indicate that that goes in this region. And then we add the 20 and we get 94, and check my arithmetic naturally. But that would go here. And now we can read the accumulated area from here through the end of any one of these trapezoids, through the end of any one of these endpoints of the intervals of partition. Then we do something, so here I say accumulated areas are 34, 34 plus 28, and dot, 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 and then the final one would be 34 plus 28 plus 12 plus 20. Okay. Another thing we label is the rate of slope change. Okay, every time the slope changes, that is, at the end of every one of our intervals of partition, our subintervals in our partition, the slope is going to change. Now, that maybe it won't, because maybe the slopes stay the same, but generally we expect the slopes to change. So we calculate the rate of slope change. How do we do that? We find first the change in slope. Now we had to spend a little time explaining again why the change in a quantity is its final value minus original value, because people want to do the original value minus the final value. That doesn't make any sense if you're finding a change in temperature, which might go up or down. It doesn't make any sense if you are doing any quantity that might go up or down, finding the change in any such quantity. You always subtract the original value from the final. And you think about temperature and ask yourself if the order in which you're subtracting makes sense. So it doesn't make sense unless you do this. Okay, so the change in slope here is what? Well, at the first point where the slope changes, which would be the end point of your first subinterval of your partition, the change in slope will be the final value, which is negative 3/2, the slope that you end up with, minus the slope you started with. So we get this, it's negative 9/4. The rate of slope change will then be that divided by the length of the interval. Why do we use the length of the interval? Because the slope on each interval will be probably, most likely, if the function, if our intervals are short enough, pretty close to the slope at the midpoint of the interval. So for the interval from 2 to 6, the midpoint is 4, slope is 3/4. Midpoint of the interval from 6 to 10 is 8, the slope is negative 3/2. From 4 to 8 is 4 units, which is the same, of course, as the length of the interval. So especially if you have uniform intervals, the distance between the midpoints of the intervals will be equal to the distance between the endpoints of the intervals, the lengths of the intervals, the subintervals. So we divide the negative 9/4, which is our change in slope, by 4 of the length of the interval. We get negative 9/16. Now, I put pointy brackets, like a less than sign and a greater than sign, but it's just thought of as a way of enclosing this in a set of symbols. It's different than parentheses, different than a circle, different than a rectangle. And we label that here above the point where the slope changes. Then we do that for this and this. So it's a very simple, straightforward process. Okay, first thing we looked at, but this is very important, and we'll find out more over the next couple of days why. Okay, then you have the next thing. We're leading up to the definition of the sine and cosine function. We define the sine and cosine function in terms of a unit circle. So right now we're just going to look at the unit circle and ask about the arc length on a unit circle. Okay, the arc length is the distance you would travel from one point to another. Now, in defining the sine and cosine, we're always going to measure, for any point, we're going to measure the position of that point by the distance you have to travel along the arc to get from the positive x-axis point, 1, 0, on the unit circle being a circle of radius 1, okay, from this point to that point. So if we wanted the arc length position corresponding to this point, we'd calculate the arc length from here to here on the unit circle. Now, it's easy to calculate arc lengths on the unit circle for certain points, okay? And we're going to actually calculate it for the points that correspond to your 12-hour clock. It's very convenient, and you get a good picture of the sine and cosine function. You've already done graphs of that nature, so this should be pretty easy to understand, but first let's get the arc distance. Okay, we know the arc distance around the whole circle is 2 pi. Why is that? Now you go back to the most basic definition. The definition of pi is the ratio of circumference to diameter of a circle. That is, circumference of a circle divided by the diameter. That's what pi is. So, what's the arc distance around the whole circle? Well, around the whole circle, the distance you go is, is what? Pi times the diameter, isn't it? Okay? So it's pi times the diameter of the circle because of the definition of pi as ratio of circumference to diameter. That means if you multiply the diameter by pi, you're going to get the circumference. Okay, then since the distance, the distance around the circle is 2 pi times the diameter, it's pi times the diameter. The radius is 1, the diameter is 2. Sorry, it's a little late in the day. Almost supper time, not a good time. Arc distance around the circle then is 2 pi because the circumference of the circle is pi times the diameter, and the diameter is twice the radius. Radius is 1, twice the radius is 2, and that times pi is 2 pi. Okay, so, and you have a formula for that, but you shouldn't think in terms of the formula. You should think in terms of the definition of pi. It's more fundamental. Shortcut, the 2 pi r is a convenient formula for the circumference of a circle, but if you know what pi is, you don't need it. You just use pi times diameter. And understand that that is 2 pi times the radius, since the diameter is twice the radius. Okay, arc distance around 1/12 of the circle. And of course, why 1/12 of the circle? Well, for a lot of reasons, but in terms of the clock, that's the arc distance corresponding to the arc from 1 hour to the next. Okay, so 1/12 of the circle, arc distance corresponding to 1 hour on a clock, is what? Well, if the total circle is 2 pi, the arc distance is 2 pi over 12, which is pi over 6. Okay? In degrees, 360 degrees over 12 is 30 degrees. Now, the 30-degree angle, and you used to think of angles in degrees, pi over 6 is every bit as good a measure of angle as this is. Okay? Because here you divide 360 degrees by 12 because it's 360 degrees around the circle. Arc distance around the unit circle is 2 pi, and the arc distance around a unit circle is pi over 6. This is a measure of the same angle 30 degrees is. So I say pi over 6, just a good measure of angle is 30 degrees, if you take the unit circle definition. Okay, so now we'll go to the definition of the sine and the cosine. Now I just divided, right, yeah, we're doing both. Okay, So if we do 1/12 of the distance around a circle, and now you know from the clock and from everything else, that's going to divide each quadrant into 3 parts. And we're going to have points around the circle like this. There'll be 12 of them. Then we simply, and we know the numbers that go with this from what we did before and from what you did for homework. We know that on a radius 10 circle, the coordinates to this one significant figure, the integer closest to the actual coordinate at every hour on a clock of radius